You came back to learn more, and that's great. After talking about some computational models, which was just a IPO model we discussed in the first video, okay, let's talk about some architectural models, okay? So first of all, okay, we will be just discussing about the difference, okay? Overall, okay, a computational model is not a physical piece of hardware, okay? Here in computational model, we are not talking about the physical pieces of hardware. It is just an abstract set of logical rules governing how algorithms are executed on a machine. For example, IPO, input, process, and output, that is just a computational model, okay? Every computer needs to just kind of take input, then process that, then just simply output that, okay? So that is an idea, that is just a computational model, okay? Then architectural models, they'll be just discussing about how hardware works, okay? So simply, computational models dictate execution to the hardware, okay? Or simply put, it defines the blueprint for processing before physical execution takes place inside CPU hardware components. So that is computational model. And now we will be just discussing about some architectural models, which are just about the hardware and how just simply they work. Okay. Here in this video, we will be talking about three distinct architectural models, which is sequential, parallel, and multi-agent. Okay. So let's study them what they are. The first one we'll be just discussing about the sequential model, okay, which is step-by-step execution. The first thing should be done, then after that the next thing, then after that the next thing, then we just get to the result, things like that, okay. So here we have, okay, the definition. A sequential computational model is one in which instructions are executed strictly one after another from start to finish. While there may be branches in the program, for example, if-else statements or things like that, okay, the general principle is that every instruction sequentially follows the previous one. So if this is true, do the other thing. So the other thing will not happen before just kind of the if or whatever we have, okay. Everything is sequential, okay. Example, traditional programming, standard Python scripts naturally executes line by line, okay. So everything is just kind of done there. The next one, the parallel model, okay, that is simultaneous distribution. Here, as you can see here, in the modern computers, a processor can have different cores, and the main task can be just given, one part of that can be given to one core, the other part to the other core, the other part to the other core, okay? And just the result of them will be synchronized, okay? Or they will be synchronized to just produce the outcome or the output that we just want, okay. And theory is, okay, program instructions are executed simultaneously on multiple processors in order to achieve faster result. The hardware utilizes multi-core processors, example modern CPUs or supercomputers, okay. In old computers, yeah, we did not have that. There was one CPU and that CPU could just do one thing after another, okay. But in modern computers, a CPU can have multiple cores, or even in some computers we can have just multiple CPUs, okay. So we can distribute the different parts of an execution or a program to different cores. And we have gotten an overhead here, okay, because beside doing what computer needs to do or what the program needs to do, there has to be some calculations and some controllings or things like that to manage distribution of this jobs to different cores, and at the same time synchronizing them, okay. So that is an overhead, okay. Overhead requires strict physical and software requirements. The explicit operating system must support it using specialized softwares for task synchronization. So that is just an overhead that it needs. Then we just come to the multi-agent model, okay, autonomous cooperation. In multi-agent cooperation, okay, we have just gotten different agents who just work entirely separate and just individually for themselves, okay. But then there are some negotiations or some communications and connections between these protocol or between these agents that synchronizes them, or just that through those negotiation protocols or negotiations, they try to generate one output, okay, true and a complete output somehow. So see the definition: a model in which independent computer systems or agents cooperate and coordinate with other agents to achieve their goals. So here, each agent is autonomous. It means self-directed. Agent A is just works with its own rules, its own hardware. So completely that is just self-directed, okay? And operates under its own control. Now, interaction, how they are just interacting with each other. So agents cooperate strictly through negotiation and coordination. Okay, so they communicate with each other. They just take information from each other, okay? And they just coordinate their results, things like that, okay? This forms the basis of modern artificial intelligence, okay? Swarm robots. So right now, the base of artificial intelligence is just something like this, okay? The multi-agent model. See a real world example or metaphor for that, okay? The holiday booking agent. So the airline agent, hotel agent, transport agent, each one of them, they just work independently, okay? They are autonomous. Each agent controls its own pricing and availability independently. So airline agent just checks the prices of the airline, the availability or things like that, okay? Hotel agent just does the same thing for hotels, transport agent, okay? Anything. Then there is just what? Negotiation. The agents cross communicate preferences to find the best package price without direct human involvement. Simply, I want a detailed holiday description, okay, or things like that. Then these agents will just, each one would work separately and they will just communicate with each other to just find the best possible pricing or just result for me, okay? In coordination, okay, they synchronize dates and times to ensure the flight arrives before the hotel booking begins, okay? So they will just coordinate with each other that everything just works smoothly. That is just a real world example for that, okay? So the multi-agent model kind of just works like this. Then see here, in this slide, we are just talking about the scalability, okay, and concurrency, okay. As the number of cores develop, so we have parallel models or the multi-agent, okay, the speed of the programs increase. But then there are just some things that, yeah, not every software can be just parallelized or kind of work in multi-agent softwares, okay? So the first problem here we might have is just kind of data dependency, okay? So scalability is severely restricted by logical dependencies. And what that means? It means if instruction B relies on the mathematical output of instruction A, they must run sequentially, okay? If the result of this instruction A is used in instruction B, so instruction B cannot run at the same time or before instruction A, okay? So that is just one problem, so we have to just think about. And the other one is, okay, physical capacity, okay? So true concurrency is physically dictated by the hardware's capacity, number of processing cores, and bandwidth of internal buses. So if we have just gotten less number of cores or the bandwidth is just kind of limited, again, that limits the scalability and concurrency, okay? So that is the thing. Remember that, okay? You cannot parallelize a task that is sequentially dependent, regardless of how many cores you throw at it, okay? You can just have a very powerful computer with many cores, but if the tasks your computer needs to do, they are dependent to each other, okay? You cannot kind of just make them parallel or just give them to different cores, okay? So you don't have to forget that. Then a small comparison between sequential, parallel, and multi-agent, okay? So the first one, control architecture. How are they controlled, okay? In sequential, the control is completely centralized, okay? We have gotten a single thread in a single CPU, okay? In parallel, it is centralized. Again, it is controlled by the operating system scheduler. But in multi-agent, that is decentralized and autonomous, okay? Every agent works with its own control, with its own architecture, okay? So here that is decentralized. Execution flow in sequential, so we know that is linear and step by step, okay? Everything is just done step by step. In parallel, simultaneous and synchronized. Many parts of the program can just run at the same time, just simply they need to be synchronized, okay? And in multi-agent, that is completely independent, okay? And simply they are cooperative. The first agent will do his thing and will just communicate with the others or just give them information or take information from them to just get the best possible answer, okay? But the execution or the execution flow is completely independent, okay? Then system overhead, extra thing that your computer needs to do. In sequential, that is minimal, kind of none, okay? Just simply computer does whatever it's told. In parallel, it's high. Why? Because that synchronization, that takes time, okay? So operating system synchronization is just extra work that computer does. And in multi-agent, okay, that is kind of the highest. Why? Because yeah, there are just complex negotiation protocols, okay, between the agents and the coordination or things like that. They just take time. So that is a complete overview of the three architectural models. We just got to the questions, okay? What exemplar? 6 marks, for example, this has, okay? Compare and contrast the sequential, parallel, and multi-agent models of computation. So based on what we have studied yet or just we discussed in this video, okay, pause the video, write your answers, then play the video and compare your answers with what we have here. Good. Let's see the answers, okay? So first of all, similarities, the compare marks, okay? So highlight that all three are abstract logical models governing algorithmic execution. So they are all abstract logical models, okay? All three require initial physical hardware, CPU memory, to eventually execute their operation. So they cannot work without CPU and memory, okay? And then just discussing about differences. Execution order, okay? Sequential runs sequentially, one after another. Parallel runs simultaneously, okay? And for example, hardware parallel explicitly demands multiple processors or cores. Sequential runs on a single processor, okay? You can just talk about the multi-agent as well. Yeah, multi-agent works on different computers. Coordination, multi-agent requires autonomous programs to negotiate and cooperate to achieve a goal, unlike the rigid centralized OS controls of parallel processing and sequential, okay? So that is kind of the answer you can give. And for your exam, you have to just remember these things, okay? The first one, okay, the multi-core trap. If your computer has multiple cores, it does not really mean that, yeah, your software will run faster, okay? Because there are other things as well needed, okay? A sequential program does not automatically run faster on a modern CPU. If your program is programmed, okay, sequentially, if you just run it on a supercomputer as well, it will just run one after another, okay? So hardware cannot magically force a sequential algorithm to run in parallel without explicit operating system synchronization and parallel programming logic. So the software has to be made parallel by the programmers when they are just writing the code, okay? Otherwise, even if you have just multiple cores as well, only one core will be used, okay? And you just have to remember another thing as well, okay, that vocabularies or keywords are really important for the exam. So you have to remember these words, okay? Autonomous, that is systems act independently and or self-directed, okay, in multi-agent. Then negotiation, simply it means agents discussing and adapting to reach a functional agreement, that is negotiation. And coordination, organizing different autonomous activities to work together effectively, okay? So that is just coordination. You have to just remember these words. And that's it. Wish you all the best. Good luck and goodbye. See you in the next video.